Let's look more closely at how we're going to calculate properties for saturated mixtures, which would be, we would find that those states underneath the vapor dome. Let's look at the first part of a two-part problem. We have 4 kilograms of water at 100 degrees C, and it fills a closed container. Let's just call that a rigid tank. And that tank has a volume of a cubic meter. Now, if the water at this state is a vapor, they want us to determine the pressure. But if the water is a two-phase liquid-vapor mixture, they want us to determine the quality. So we first need to determine what state this is, or what phase the state is in. So here's what we were given. We have a mass of 4 kilograms. A volume of the tank is 1 cubic meter, and the temperature of the water inside is at 100 degrees C. So let's go to the saturation table at 100 degrees C, and we're going to grab some values. The specific volume of a saturated liquid is given in the table at 100 degrees C. The specific volume of a saturated vapor at 100 degrees C is given. We've got both of those down here. And we also noted that the saturation pressure at 100 degrees C is 1.014 bar. Now, we know that the definition of specific volume is that it's simply volume divided by mass. Now, notice I put a subscript X on these variables. The reason is we can put any number of different subscripts on this equation and it will be valid. So for instance, I could put a T here for total, in which case I'm saying that the specific volume of the total mixture is equal to the total volume that the mixture fits in divided by the total mass. Or I could have put a G in here or an F in here. So if I had an F, I would say the specific volume of a saturated liquid is equal to the volume of that saturated liquid divided by the mass of that saturated liquid. So we find that this is a very useful equation and we can use lots of different subscripts. Let's again use total. So we're looking at the total mixture. The specific volume of the total mixture is the total volume, which is the volume of our tank of 1 cubic meter, divided by the total mass of water in the tank, which was given as 4 kilograms. So I know the specific volume of the mixture is 0.25 cubic meters per kilogram. Now let's compare this value to the values of V sub F and V sub G at this temperature of 100 degrees C. And we can see that our specific volume of the mixture is in between. It's more than V sub F and less than V sub G. So that confirms that this state is a saturated mixture. So let's determine the quality of the state. The quality is given by this formula. It's the specific volume minus the specific volume of the saturated liquid divided by the specific volume of the saturated vapor minus the specific volume of the saturated liquid. Well, we calculated a value of specific volume for this mixture at 0.25, and if we plug in our values for V sub F and V sub G, we get a quality of 0.149 or 14.9%. So let's plot this state on a TV and a PV diagram. On a TV diagram, a pressure line, a constant pressure line goes up to the right. And we know at 100 degrees C that the saturation pressure is 1.014 bar. And so those are going to overlap under the vapor dome. And since X, or the quality, is 0 at the saturated liquid line and it's 1 at the saturated vapor line, 15% is going to be down here somewhere. And I'll show that. The specific volume of 0.25 is greater than V sub F and less than V sub G. Now on a PV diagram, the temperature line goes down to the right. Okay, and so that temperature would be 100 degrees C. The saturation pressure at 100 degrees C is 1.014 bar, so those lines overlap under the vapor dome. And a 15% quality is going to plot right about here, because quality at this on the left side of the vapor dome is 0, and on the right side of the vapor dome is 1. So 15% would be right about here. Let's look at the second part of this problem, which says that ammonia is at a pressure of 40 psi, and it has a specific internal energy of 308.75 BTUs per pound mass. We want to determine the specific volume at this state in cubic feet per pound mass. Now remember, any two independent properties define a state. So here we have two. We have 40 psi, and we have the internal energy. So that is what we were given, and that will fully define the state. So let's go to the saturated ammonia table at 40 psi and find the saturation temperature at this pressure, which is 11.65 degrees Fahrenheit. So now we can get different values from the table. We can get V sub F and V sub G, so we can get the specific volume of the saturated liquid, and we can get the specific volume of the saturated vapor. We can also get U sub F and U sub G. We get the internal energy of the saturated liquid is 54.89, and the internal energy of the saturated vapor is 562. So let's calculate the quality. We don't have to use specific volumes to calculate quality. We can use any properties. As long as we have the property of the state, and we have the property of the saturated liquid and the property of the saturated vapor. In this case, we can use the internal energy to calculate quality. So we've got quality is U minus U sub F over U sub G minus U sub F. Well, U, the quality, was given as 308.75. That goes here. And then we have U sub F here and U sub G here. In this case, we calculate a quality of 50%. We can use that now to determine the specific volume. We know that the specific volume is the specific volume of a saturated liquid plus the quality times the difference between the specific volumes of the vapor and the liquid. So we have all of those values, and we can calculate the specific volume as 3.533 cubic feet per pound mass. We can draw the TV diagram and the PV diagram for this state. Remember that on a TV diagram, pressure goes up to the right. So our 40 pressure line overlaps its saturation temperature of 11.65 degrees Fahrenheit under the vapor dome. And a quality of 50% would be right between the saturated liquid line and the saturated vapor line. On a PV diagram, constant temperature line goes down to the right, and we know that at 40 psi, the saturation temperature is 11.65 degrees Fahrenheit, and so we can plot our 50% quality right in the middle of the vapor dome.